We're going to take a look at how to find the volume of a solid generated by a region. I recommend hitting pause and reading this question. Okay, here's a picture that corresponds to this problem. This is the two-dimensional region R referenced in the problem. Imagine that this region R were rotated or spun around the x-axis in a way that it created a three-dimensional solid. You can see that three-dimensional solid here, and that is what we're going to be trying to find the volume of. One of the key elements to finding the volume of this is to take what's called a cross-section, and then to find the area of that cross-section. As you'll see later in this video, finding the area of a cross-section of a three-dimensional solid that we're trying to find the volume of could be very helpful. But what do we mean by cross-section? After all, aren't there infinitely many cross-sections of this thing? Yes, in fact, there are. And what our goal is going to be is to take one particular shown cross-section, call it occurring at a particular x value, but rather than picking a number, just saying that it occurs at x, and then thinking about x as being any number between 0 and 4, we can simultaneously, by this one diagram, consider all possible cross-sections of this region. So what we're going to do to find the area of it is we're going to use the area formula for a circle. After all, if we got this region by spinning something flat around the x-axis, almost as if we were holding the x-axis and twisting it, then every cross-section is going to be a circle, and therefore I can use pi r squared to get the area of this cross-section. What I need to find now is the radius of this particular cross-section at an x value of x, thereby really finding all the areas of the infinitely many cross-sections. So as you know, the radius of a circle extends from the center to the edge, but wouldn't the radius of this circle just be the same as the height of the radical x function? And therefore, the radius is the function itself. And this expression on the left represents the circular area of any particular cross-section as x ranges from 0 to 4. And now what we do is we integrate from the left to right boundaries of this shape the area of each particular cross-section. In some sense, the act of integrating is like adding. And what we're doing when we integrate the area formula for a cross-section is we are in some sense adding up all infinitely many cross-sections. And that, in a way, gives us the volume of the shape that we're looking for. All we have to do now is actually perform the integral. I've done that right here. Feel free to hit pause and analyze the math. It's not all shown. And what this shows is that the volume of this three-dimensional solid is 8 pi. In general, when we have other functions, we can say that the volume formula would always be the integral of pi times that function squared, and that will give you the volume of any kind of three-dimensional solid revolved around the x-axis that you're trying to find.